Alright, so let's talk about Frenet-Serret frames, or TNB frames. So first we're going to let C be a curve that is parameterized by r of t, as we have written right there. And then we want to define three vector-valued functions related to our curve. First of all, we have the unit tangent function, which all that is the derivative of the parameterization normalized. Keep in mind that the name really spells out what this is. We know that the derivative gives us a tangent vector, and all we're doing is making sure that this is a unit vector, so it's scaled to length 1. And then if we take the unit tangent and differentiate that and normalize the result, then we get the unit normal. So unit normal is the unit tangent's derivative normalized. Let me at this point draw your attention to the fact that there's a difference between taking the derivative and computing the length versus taking the length of a function and computing the derivative. Those things are never, or well, I shouldn't say never, but they're very, very often not equal to each other. So keep in mind that although we might like to think that the unit normal is maybe the second derivative normalized, that is not in fact the case. The unit normal is not the second derivative normalized. It's the derivative of the unit tangent normalized. Okay, usually a lot more complicated than the second derivative normalized. All right, and then the third vector that we want to mention here, the vector-valued function, is the binormal. So the binormal is just the cross product of the unit tangent and the unit normal. So let's first, before we'll eventually do an example, but to begin with, let's consider the basic properties of these guys. Okay, so first of all, the unit tangent is in fact a unit vector. That should be obvious, just like it's the same case with the unit normal, because they are a vector-valued function, but they've been normalized. Then the next thing to notice is that since the length of the tangent is constant, what we end up with is that the unit tangent and its derivative have to be perpendicular to each other. We proved this before. Notice that t dot t being a constant, if we differentiate that using the product rule, we have t prime dot t plus t dot t prime, and the derivative of 1 being 0, then this then implies that 2 times t dot t prime is 0, canceling off the 2, we end up with t dot t prime is 0. So we already have that the unit tangent and its derivative are perpendicular to each other. Okay, as is true of any vector-valued function of constant length is perpendicular to its derivative. But then keep in mind that the unit normal is really just the unit tangent's derivative rescaled. So the unit normal and t prime are parallel to each other. So you put that together, and this tells us that t and n are perpendicular. Okay, so now we have two mutually perpendicular unit vectors. Let's come down to the binormal. Well, the binormal is t cross n, so obviously that is perpendicular to t and is perpendicular to n. So now tn and b are all mutually perpendicular. We would naturally want to then ask, what about the length of the binormal? Okay, so remember, binormal is the cross product of t and n, so take the length of a cross product. We have this nice formula that the length of a cross product is length, then sine of the angle between those two vectors. But t and n are perpendicular, so the angle between them is 90 degrees, pi over 2. Then t is a unit vector, n is a unit vector, sine of pi over 2 is 1, and so we just discovered that b is also a unit vector. By the way, an alternate way to see this is that if you take t and n, they're perpendicular to each other, so they span a rectangle, specifically a 1 by 1 rectangle, because they're unit vectors, so they span a square of area 1. Remember that the cross product's length is it gives the area of a parallelogram spanned by those vectors, and so another way to see that the binormal's unit vector is just that the area of the corresponding parallelogram actually is just the area of a unit square, so it's 1. Okay, so let's go ahead and clear all of this mess out of the way and remind ourselves of, we'll go back up above and remind ourselves of what we just learned. Okay, I need to get better at erasing things. All right, okay. Oops. Okay. So what we now know, coming back up here, is that T, N, and B are all unit vectors, and T, N, and B are mutually perpendicular. Okay? In fact, what you can start to think of is that maybe we have some sort of curve. We can start to think of the unit tangent. This gives us a unit vector pointing in the direction that our curve goes. So it kind of tells us what forward is. The unit normal, it tells us how the unit tangent is changing. So it tells us kind of how the unit tangent's turning, and essentially it's telling us what left might mean. And then finally the binormal, remember this is perpendicular to those two, it's really telling us up. So we can imagine we're some probe heading off through space, and maybe this curve here is our trajectory. Well, T is going to give our probe a way of knowing how to think about what forward should be, N being left, and B being up, and it's giving us a traveling coordinate frame. And of course, if this works for this particular point on a curve, and we have different answers at other points. All right, let's look through a specific example. Okay, so we'll take the simple example of R of t is, let's do 3 cosine t, 3 sine t, and 4t. Okay, I'll make that look more like a t. Oops. Okay. All right, then we take the derivative. This will give us a vector that's tangent to our curve. Okay, so minus 3 sine t, 3 cosine t, and 4. Then we need to take the length of our derivative. This, of course, would be the square root of, we'd have 9 sine squared plus 9 cosine squared plus 16. But we can factor 9 out of next to sine squared and cosine squared, and we know that cosine squared plus sine squared is 1, so this just leaves us with 9 plus our 16. That's 25, and the square root of 25, of course, is 5. So what do we end up with? That the unit tangent is r prime normalized, so it's 1/5 times minus 3 sine t, 3 cosine of t, and 4. All right, next, the unit normal. Okay, so let me go ahead and erase above here. So I give myself some room because I want to put the normal right below the tangent. Okay. All right, so the derivative of the unit tangent is 1/5, just a constant coming out there. We have minus 3 cosine of t. Derivative of sine is cosine. Derivative of cosine is minus sine, so we have minus 3 sine t is the second component. And then the derivative of 4 is 0. Okay, if we take the length of t prime, Well, we have this 1/5 constant out front, and then what are we left with? Well, actually we can take out an additional 3/5. Maybe I'll write down an intermediate step. So we have, if we factor out this -3 as well, we have cosine. We have cosine sine 0, taking the length of that, and we could take the absolute value of the -3/5 that came out. We have 3/5, and then the square root of cosine squared plus sine squared plus 0 squared, and that's just going to be 1. Okay, so what is the unit normal? Well, it's the derivative of the unit tangent normalized. So we're taking t prime and dividing by its length. Notice all that does is cancel off the 3/5. So what we're left with is minus cosine of t minus sine of t and 0. Okay. Finally, we want the binormal. Binormal is t cross n. So we're just computing a cross product. Remember, the cross product's bilinear. I'm going to take this constant and pull that out. Okay, and then we need to compute the cross product of what's left. Now remember, we imagine I, j, k, and our 3x3 determinant we're computing. The I component comes from considering the final two columns. So we end up with going down, we have a 0, and going up, we have a minus -4 sine t, so that's just 4 sine t. Now the j component, we look at the first and the last components, imagining that we're crossing out j's row and column, and so we're left with 0 going down, and then going back up, we have minus a negative, and we get positive 4 cosine, but it's the j component, so it gets a minus sign. So we have minus 4 cosine. And then finally, the k component, we for that, we just consider the first two components here, and this going down, we have 3 sine squared. Going up, we have minus a minus and get 3 cosine squared, but 3 sine squared plus 3 cosine squared is just 3 times sine squared plus cosine squared, which is 3 times 1, so it's just 3. Okay, so there we go. There's our TNB frame. Okay. All right, and if you checked, the binormal is indeed perpendicular to T and N. You could dot. Okay. There's lots of other examples we could do. Let's just stop here with this and point out that if you go to my web page and look under Maple examples, what we can see here on the this animation is a vector in red, green, and then I guess it's gray or black or something. Anyway, the red vector there is the tangent, the green is the normal, and the other vector is the binormal. It's being drawn at various points on that curve. If you're interested, scroll down to multivariable calculus here, and if you want to look around arc length curvature and TNB frames, see if it will follow that link. If we scroll through, we can find examples of TNB frames being calculated in Maple. So there's a TNB frame for a particular curve, which turns out to be nothing more than an ellipse. Anyway, there's lots of examples through here, and we'll look at some other topics like curvature and such in the future. Okay, thank you.